Hi, Mrs. Pone here. This is video 2 of our Big Bang series, and last time we were talking about this this almost absurd idea that everything in the entire physical universe was once compressed into something tinier than a pinhead, something the size of an atom, even smaller, and it all expanded from there. And that's a fantastic idea, and there's got to be some really strong evidence for us to buy something like that, and there is. A lot of evidence for the Big Bang. But this is video series 2. Before we get into the evidence for the Big Bang, the three major evidences, we are going to do a little supplemental learning on light and waves and something called the Doppler effect, because we need that to really understand redshifting galaxies, and really any astronomy in general basically depends on light. So here we go. In the last video, we did talk about general relativity a little bit, and we said that general relativity is really what first paved the way for this idea that the universe itself could be expanded. A very highly tested and successful theory in science, one of the best there is. So let's just jump right into light. Here we have a full image of the electromagnetic spectrum. This should be reviewed, so I don't want to spend forever on it, but realize that there's many different types of light. Gamma rays, X-rays, ultraviolet rays. I'm going to throw the mouse on. When we look right here where the mouse is, visible light, which is blown up here, only encompasses a very small portion of all the actual light there is. And the type of light really just depends on the wavelength and frequency of the wave. Light is a wave and the particle, but we're not really worried about that right now. But if you look on this side of the electromagnetic spectrum, you have increasing wavelengths. There's a larger distance between each crest of the wave, and over here it's getting shorter. So we have our really high energy ionizing radiation here. These gamma rays, X-rays, ultraviolet rays cause skin mutations, cancer. UV rays, of course, either you can get cancer or tanned or both at the same time. Infrared, you're kind of like heat vision kind of things. Your microwave, how we actually cook. Microwaves are the perfect size to vibrate water molecules, to make water molecules move around. So that's how a microwave works. And we have radar and radio waves. So there's a whole bunch of different types of light. And astronomers don't just stick with what we can see. We need to analyze things using all these different types of light. So just realize that light has a specific energy. Different colors have a different frequency, a different wavelength. Blue light has high energy. Red light has low energy. It goes from low to high, and it follows that Roy G. Biv thing. If you heard of that name, Roy G. Biv, ROYGBIV, red, orange, yellow, G, green, Biv, blue, indigo, violet. If it's a way to remember the colors of the rainbow. So just please realize that there's a whole bunch of different types of light, and each type of light has its own different amount of energy. And also from chemistry or maybe even physical science, you learned a simple 2882 rule before you learned a fancier way of writing electron configurations, and you put electrons in these rings around an atom. These are Bohr or shell diagrams. And we know that light can form when energy comes in. Basically, if some energy comes in and strikes an atom, then this electron right here could become excited, or any electron or a bunch of them. It jumps up to a higher energy level. It leaves its ground state. It actually goes back down. You can see that process goes up and down. Because it's unstable there, but in order to drop back down, it has to re-emit that energy, and it does so in the form of photons. So we know that when materials are excited, they emit a certain type of light. Now, the type of light they emit could be visible, could be blue, could be red, could be green, could be ultraviolet. It depends on the atom itself. What's its nuclear charge? How many shells are there? What's the electron shielding like? All these terms from chemistry. So different electron jumps and transitions are going to produce different types of light, photons, quantized photons with different energies. So this leads us to the question of, how do we know anything about space? The sun is 93 million miles away. In fact, it takes the light about 8 minutes to get to us. If the sun disappeared right now, we wouldn't know about it for 8 minutes. We can't go to the sun. It's really hot and it's really dangerous there, and it'll warp anything we pretty much send at it. So how do we know what the sun is made of? We know a lot of things about the sun. We can't actually put sun stuff in a test tube and, measure and do some crazy mad scientific experiment. So how do we know about space? Well, naturally by analyzing light. And if you see this picture up here, you may have seen one of these or a circular version of this. It's a basic spectroscope that we would use in a classroom. And you know that when white light is passed through a prism, it breaks into a rainbow of colors. White light is made of all colors. Well, these tools have something inside called a diffraction grating, and when you use them to look at something, it breaks light into a spectrum of lines, a set of spectral lines. So just please realize this, that the element helium, the second element on the periodic table, it was discovered on the sun 93 million miles away before it was ever found on Earth. People were using spectroscopes and they saw this yellow line on there and it didn't correspond to any known element at the time. So basically, they figured out it was a new element. And as it turns out, almost 30 years later, helium was discovered on Earth. Realize that around this is the time that Mendeleev first published his periodic table. All the elements weren't discovered. The periodic table wasn't fully complete. So, spectroscopes were used to find out missing elements or new elements or things like that. And also, helium's an interesting thing. We're going to do a little side video after this one on helium and fission. Helium is not gravitationally bound to Earth, which means it's really, really light, so we actually lose all our helium to space. It's replaced by radioactive elements in the crust, and it's non-renewable. When we run out of helium-producing elements in the crust, we run out of helium, and it does have some practical applications. But helium was discovered on the sun before it was found on Earth, which is pretty remarkable. In chemistry or physical science, you may have used a spectroscope tube, basically a tube filled with gas, maybe hydrogen, maybe neon, whatever gas you have, and you electrocute the ends of it. It's kind of like cathode ray, J.J. Thomson, remember the electron? And if you use one of these spectroscopes with a diffraction grating inside and you look at it, it will break the light down into these sort of spectral lines. You'll get a pattern. Each element will give off its own unique set of spectral lines. So we can actually identify elements at a distance just by analyzing their light. We can see what's in a star by pointing a spectroscope at it. Every element gives off its own unique set of spectral lines. This is very, very important for understanding the Big Bang and evidence for it. So just to take a quick look at the hydrogen atom, the Bohrrittenberg Model, we have 6 energy rings. You have a nucleus, 1 proton, hydrogen atom, 1 electron. It's a neutral atom. If this hydrogen atom absorbs energy, we know this electron can jump up to a higher ring, and then that electron can fall back down to a different ring. So I just want to show you what happens for different electron drops, because they're not all going to produce the same type of light. We have the visible or Balmer series. If an electron is excited, and it jumps from, say, ring 1 to ring 6, and then let's say it falls back down just to ring 2. Well, that's going to make visible light, 410 nanometers, purplish. If it jumps from ring 5 to 2, you're going to get sort of a blue-purple light. If it jumps from 4 to 2, you're going to get a blue-green light, 486 nanometers. And if it jumped from 3 to 2, you're going to get red light. Each jump in an atom corresponds to a different type of light. It doesn't all have to be visible. You could be ultraviolet jumps. If you go from ring 2 to ring 1, that's UV. Ring 3 to ring 1, UV. Ring 4 to ring 1 is UV. So an excited hydrogen atom can give off many different types of light, different colors of light, or different types altogether in terms of ultraviolet, or even can give off infrared, depending on the jump. So there's certain jumps that when they jump back down to energy level 3, they give off infrared light. So different electron transitions or jumps correspond to different sets of light. And this right here is hydrogen. You can actually see the spectral lines on hydrogen. That's kind of blocking it right there. So you have right here, line one of these lines is a little bit hard to see, but you can see the red line right over here. Then there's the blue-green line right there. Then you can just see one more line over here. It's kind of hard to see the fourth line for hydrogen, but this is basically what you're seeing when we look at these objects through a spectroscope. We're able to identify the element based on their spectral lines. Each element has its own unique configuration of electrons, its own nuclear charge, effective nuclear charge. So there's going to be different energies when electrons transition down in different types of light. And we have a very good understanding of this science, and this is what allows us to basically do astronomy. All right, so what we do need to realize is that there is something called the Doppler effect, and we're going to make use of these spectral images. Very important, very, very much. They're very crucial to understanding the Big Bang and the Doppler effect. So the definition of the Doppler effect. This definition is a mouthful: a change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source. You probably got to read that 10 times and let it sink in. It does come from Christian Doppler, who described the phenomenon in 1942. Basically, we've all heard an ambulance passing by, and as the ambulance gets closer to you, the pitch of the sound gets really, really loud. It's almost like ear piercing. It hurts. But then as it moves away from you, the pitch kind of gets very, very low, and it's not as intense to sound. That's actually the Doppler effect. Here's a picture kind of showing it. You have a car emitting noise. Initially, the waves are equidistant from one another. Look right here. The noise is coming out. Each of the waves is equidistant. Then once it starts moving towards something, what happens to the waves? The distance between the sound waves bunches up. So as it's moving towards you, the waves are closer together. They have shorter wavelengths. And what happens behind the car? Well, the waves, sound waves, stretch out. That is actually the Doppler effect. The wavelength changes as an object's moving towards you, the waves get closer together. As the object is moving away from you, the waves get further apart. So another little image to see that. This police car siren is moving towards this individual to the right. The siren waves bunch up, so there'll be a very loud pitch. Behind them, they kind of drag out or extend, so the pitch will be very, very reduced. And you can look up ambulance videos if you don't remember what an ambulance sounds by as it drives by. They're all over YouTube. But what I want you to realize is light is a wave, just as sound is a wave, and light behaves just like sound. Light obeys the Doppler effect. Definitely obeys the Doppler effect. So keep that in mind. I think we're going to end this video here. We are going to talk a little bit more about the Doppler effect in a future video. Just realize that light sources are altered. If a galaxy is moving away from us, its waves are going to stretch out. If a galaxy is moving towards us, its waves are going to come closer together when we look at its spectral lines. And this is going to be very, very important to us. So just a very brief overview of light, how light's created, where we get spectral lines from, spectroscopes, how we analyze stuff in astronomy, and a brief introduction to the Doppler effect, which we will continue with in a video or two from now. Mr. Sapone, I'm out.